Now we're ready to form our connections, and we'll do that in 2 steps. First off, we'll connect everything, and then we'll draw the actual route that connection is going to make through the circuit board. So to connect things, we need this tool here called Connect Pad to Pad. We'll just select that and then select the 2 things that need connected. And I'm going to put an incorrect one in here first just to express this point. So we click the first pad and then the next pad that's going to be connected to. And the point I wanted to make is that is not a line. We're just seeing a line that represents a whole lot of data about the circuit board we're putting together. So if I come in here and try to select that, because that's the wrong line, to delete it, I can't just select it. But if we get an incorrect line and want to get rid of one, notice it's in 685. So that's that's connection 685 out of the network we're putting together. Just a number the computer gave it. So that's actually the line we see is just representative of the actual data. If we want to get rid of it, we have to click one of the pads, and then over here in the properties, we'll see the net property, and we have to actually delete what's in that box to get rid of a pad, to get rid of the connections. I just wanted to make that point. So now we can go ahead and make the connections. So I'm going to start here with all the connections for the pull down resistors. So switch 1 will connect to resistor 1. Switch 2 connects to resistor 2. Switch 3 connects to resistor 3. And switch 4 connects to resistor 4. And now all of these need to go back to a ground. So over here on the Arduino, I have a ground right here. So the other side of the resistor is going to come over to this ground. And it wants to know if I want to merge those. Yes. Again, this resistor is going to come to ground, and notice how it formed that better connection than the one I actually drew there. So I'll click on the resistor, bring it back to ground, and when I click, it formed a better connection than the one I drew. So again, bring this all the way back to ground and let it connect up that way. So now all the pull down resistors take the excess power from the switch right back to ground to dissipate that when we're not doing anything. And we can do the same thing with our plus 5 volts. Bring that to all of the voltage in lines on those switches, the VCC. Yes, merge those. And notice I'm going back and making the actual connection each time. I'm going to let the computer do that better connection. That goes to the voltage in, and that goes to the voltage in. Did that connect correctly? Yep, and just watch this very carefully. Make sure you have all the right connections. And remember, we're not drawing a line here. There's a lot of internal data, so if you need to delete it, select one of the pads it's connected to and delete it from that network. So it's going to be that process to form all the connections that are also made over here. So I'm going to repeat that process with the video paused, and I'll be right back with the finished version. I suppose I could throw one more step in here for the process. So to hook up switch 1, I'm going to come over to the schematic, and here's switch 1. And if I hover over that line, it's going to change colors so I can see more clearly that the plan has switch 1 connected to pin D4. So then over in the PCB, I'll come over here, select the connection tool, and make that connection. So from the signal up to pin D4. And I'll do all of them that way, making sure it exactly matches the schematic, and just come over here and hover over the line, and you can see both ends of the connection. So switch 2, we can see goes to D5. And I'll go ahead and make all these connections and be right back. And now with all the connections made, we need to figure out what the actual copper route those signals are going to take through the PCB is. And it probably won't be too bad in this case, but sometimes that can be a little tricky and might take more than one try. So I always like to set up the network connections and then do the actual PCB route tracing on a copy of that. So that way, if I have to start over, I can just delete the copy and go back to the network to start over. So I'm going to save this, save. And if I come over here to these, over here in the navigator window and right click on the PCB one, I'll add network onto the name here, network, and then I'll right click on it and make a clone of that, and the clone will be called routing version 1. Sometimes it takes a couple tries to, we might have to start putting it together. It's kind of like a puzzle, figuring out how we can get all the lines of copper going through there with nothing shorted out. So we might have to jump back and forth between the top and bottom sides. It's kind of like a puzzle and sometimes takes more than one try. I don't think it'll be too bad on this one, but I'm sure in our modern world you've seen much more complicated PCBs than this and have an idea of how complicated they can get. So let's get started trying to put the routing together. And I'm going to go ahead and close all of these windows. That way I know I have the right one open. All right, so got our connections, just need to set up our routes. So I just wanted to express a point explicitly here. Normally, we wouldn't put a microcontroller dev board right on a PCB like that. I'm just doing that in this case. Well, remember, the microcontroller is just the chip. So here's the Atmega 328P and SMT, the surface mount technology, the ones that just kind of get stamped on there. So that's the microcontroller, and everything else here is just some connections an engineer thought we would find useful for testing and mocking up designs. So normally, if anything, we would just order the chip mounted onto our PCB. I don't mind doing it in this case because the last time I ordered some of these from a factory straight in China, it came out to be $1.41 a piece. So super cheap, disposable. That's kind of why I ordered them as a cheap piece to put in designs. But normally we wouldn't do that, especially in a case like this, because this one, all we're doing is sending the higher low voltage directly from the press of the button, a 0 if it's not being pressed. If a 1's being pressed, then the voltage does flow through there, so it'd be a 1. So we're sending that straight in. We could easily do that from a shift register and wouldn't even need all the bits on a, Texas Instruments 74HC 165 here. Use 4 bits to just send those straight into the computer as soon as the buttons are pressed every time. And our joystick, really, we're just taking the value of a potentiometer and converting that to a digital signal. So all we would need is an analog digital converter integrated circuit, really 2 of them to handle that, which I'm apparently out of right now, but I have pulled up ready to order some more of them. And you can kind of see from the price there that ordering that chip would cost a whole lot more than these knockoff nano boards that I got from that factory in China for $1.41 a piece. But we could do just 2 of those with integrated circuits, and that would be kind of a better way to do that. Usually when we put a design together with a microcontroller, we want to try, if possible, we want to try to convert it to just integrated circuits and not use any processing power if we don't have to. And in this case, I think we wouldn't have to. We could get 2 of those, what is it? The TLC 0832CP analog. That's 8-bit analog digital converters, which would be plenty enough to handle the percentage of a joystick pushed right or left or up or down. And then this is just sending a signal through or not, either sending a signal or not. So we could run that right through a 74HC165 shift register, which takes up to 8 bits in and sends out one serial line, one serial out. So we could easily do that with one of these chips and 2 of those other chips. So we might come back and do that at the end in the proper way and kind of look at look at it that way. And then we can send the voltage straight from integrated circuits with no processing, so we could get even more speed and just automatically send that to the computer and then set up all our code on the computer side to process through that. And it would use essentially the same design, but I have these disposable nano microcontrollers right now, so it does make it a whole lot easier. Just if you have some cheap knockoffs of those from China that you can just throw into the final design and be done with it. It's a whole lot easier that way. But we probably will come back at the end and switch it over to integrated circuits. Just wanted to make that point. Normally we wouldn't do this, and if anything, we would just put the chip, not the whole dev board, but kind of starting out the easy way, and then we'll do it the proper way at the end.